Hey, what's going on, everybody? It's the original gamer JOYSTK, and we are back for yet another exciting chapter on programming in BASIC with the Tandy Color Computer. Alright, we're in chapter 23, and chapter 23 is introducing us to the low resolution text screen, which is complete backwards how I learned it. I learned Color Basic first when it was in a separate book and when my computer only had Color Basic. So I learned all the low resolution commands first, and I had to live with those commands and limitations for at least a year or longer before I would ever afford a better Cocoa with extended BASIC. But this book is kind of backwards. This book teaches us to high resolution graphics first and low resolution graphics towards the end of the chapter. But there's something else that's cool in here too, and that is the introduction to the joystick command. So what does the set command do for us? The set command, much like pset is on the graphic screen, is we can set coordinates. We can set X and Y coordinates. However, the resolution is much lower. On this set command here, we have 64 pixels across from 0 to 63, and we have 32 pixels up and down from 0 to 31. It takes place on the text screen, and our text screen is 32 characters by 16 lines. It's basically doubled our text characters. So each text character now has 2 pixels wide and 2 pixels tall, and it's basically a grid or a block of 4 pixels that has been squeezed into an individual text character. When you look at, for example, like underneath the F here, you notice this kind of yellow checkerboard. This checkerboard takes up the space of one of these characters here. So if you look at the F and the V, you notice that there's 1, 2, 3, 4 pixels that are squeezed into the exact same space that one text character can fit. So this low resolution graphic screen is really a mixture of text. And so literally what's happening, because I was able to print these on the screen, because I was able to print these as character strings, these literally are text symbols in color. And so you can't mix and match more than one color in one particular block here. And so what happens is that this technically represents 2 pixel coordinates, but it's one cell or one character block, and so you can't mix or match more than one color in that situation. So I could not have a red next to a blue inside this one cell, but the next cell over I could have a red next to a blue. So that becomes important when you're plotting your colors on the screen. Another thing I'll show you here real quick too is the actual grid sheet that is in the back of the book. So in the grid sheet, and now you can't see where my mouse is pointing, but in this grid sheet here, you can basically see that the character in the top left hand corner of 0, 0, those 2 top left coordinates. Those 2 top left coordinates are really one text cell that is responsible for 4 pixels. So 0, 0 in the top left, and 1, 0, which is 1 pixel over, is all part of that cell. If I go down 1 pixel to 1, 1 and 1, 0, there's a quadrant of 4 pixels that all take up one cell, one text cell, and these cells here are unable to occupy multiple colors. The only 2 colors that can exist inside one cell are black and one other color.
Hi, this is John Linville
and Neil Blanchard.
We are the Cocoa crew. I hope you're enjoying watching JOYSTK play video games, especially the Cocoa games. And when you're done with that, check out our podcast at cococrew.org.
So what the demo in the book has us do is try to put 2 pixels next to each other to kind of illustrate that concept. And when I put a pixel on position 33 right next to the one on 32, I get a double wide pixel. The minute I go to change the color here to color 4, that second color, because it's in the same cell, it hijacks both the colors and it turns them both to red. So we start off by having a double wide blue. When I paint the second blue pixel red, everything becomes red because you just can't mix 2 colors in the same cell. So in this little diagram here, they're basically saying that position 32 and 33 would be part of the same block, and vertical 14, and position 32, 33, and vertical 14 would be the same too. What's an easy way to remember this is that just remember that if you're an even number, every even number is a new text cell boundary, much like the byte boundaries in my get put demo. So 0 is one text cell, but there's 2 pixels in there. So the next odd pixel next to 0, meaning 1, would be in the same cell. 2 is a new boundary. 4 would be another boundary. 6 would be another boundary. So every even number is a new boundary where you can have colors side by side, but the odd numbers next to those even numbers cannot be a different color. Cannot match those both horizontally and vertically. So that's what that demo was trying to show us. On page 128, we get into using 4 next loops here to draw the computer's face, and this is actually really, really cute. This is a really cute demo that I do remember doing as a kid, or doing something similar to this. So what I did, rather than to go through the misery of having to hear me struggle with the keyboard, is I went ahead and I typed it all in, and then I just ran the program. So this is what the demo looks like here. It is a face that we drew a square. We've got 2 blue eyes, we've got an orange nose, we got a red mouth, and then we have a blinking eye. And we also put the word, or drew the word, hello here on the screen. So this is the result of that program. Let's step through the program and look at what the program did to do that. Right? So in line 5, we clear the screen. On line 7, we print towards the center of the screen the word hello right here. Then we start a 4 next loop for our horizontal pixels. So we start at 15, which is roughly here, about a quarter of the way in, and we go over to 48, which is roughly 3/4 the way over. So we're basically taking up about half the screen, about dead center. And we start setting that across. How does the set command work? Well, we set it by specifying our horizontal position, which in this case here, it's H, which is incrementing from 15 to 48, so it's going across. We set by a vertical position here. In this case here, we're specifying a hard-coded position of pixel 5, which is roughly 3 positions down, 3 text characters down from the screen. And then we specify a color. In this case here, color 5 is white or buff. Now within the same loop, we're doing this on pixel position 5, but we're also doing this on pixel position 20, so we're getting the top of the box and the bottom of the box in the same loop. So we have these parallel lines being driven across. Now we come down to the vertical lines, and we start on position 5, and we work our way down to position 20 vertically. So we start from the 5th pixel, and we work our way down to the 20th pixel, and then we're just basically drawing down the side. So we drew the 2 lines across, we drew the 2 lines down in one loop. So we're doing position 15, which was the left line, we're doing position 48, which is the right line, and then we finish that loop. This one here just sets a single orange pixel in the middle of the screen. That's the nose. So position 32 across, 13 down, color 8, boink, there's your nose. Now for the mouth, we're drawing a handful of pixels here towards the center. So we start at 28 and we go to 36, and we just kind of go across. We're doing color 4, which is red, and that finished our mouth. Now this one here is kind of cute because we've got a loop here. So line 130 draws the left eye. So position 25, horizontal, 25 pixels across, 10 pixels down, color 3, which is blue, that's my left eye, that remains static. Line 40 goes over a handful of pixels and draws another blue eye, but then it also resets that eye. And then line 160 goes back to 40, so it's constantly now just setting and resetting the eye, and that gives us the very cool little blinking effect here, you know. So here's old Blinky, here's old Blink Eye, and so it's kind of a cool blocky robot looking face. Believe it or not, seeing this as a kid and creating this myself for the first time was kind of a cool moment, like a oh wow moment. Wow, look what I did, this is cool, you know. So just doing that little face there, pretty cool, right? And so then it goes on to explain to us the kind of the syntax or the format of how the set command works. So set works off of a horizontal coordinate, a vertical coordinate, and a color, right? Reset, we don't specify a color. With reset, we just specify the horizontal and vertical, the X and Y coordinates, and it automatically sets that to black. Now, what if I want to determine what value already exists in a particular spot? I can use the point command. So I say point H comma V, right? So what is my horizontal, what is my vertical coordinates? Basically I'm looking into those coordinates and I'm going to read the value of whatever color is there. And then whatever I pull out of there is going to tell me what color is currently on the screen. And so this is very useful when you want to write a game, a simple game to do collision detection. Like one of the earliest games I wrote was kind of like a snake game, or like the Tron light cycle game, where you draw a line in a different direction, and as you go you have to avoid touching your own tail. Well, how do you tell if you've touched your tail, or how do you tell if you touch something else on the screen? Well, you have to grab the color. You have to grab the color of that coordinate. So before you put the next block down for the face of the snake or the next part of your light cycle trail, you kind of take a peek at that color. You get the value of what color is there. If the color is 0, you know you're heading into a black space. If the color is value is anything else, then you've got something there, and then that was going to help you determine, did you crash into yourself, did you crash into something else? So being able to grab the color value from the screen, very cool feature. Now, another thing this chapter gets us into, which is very important thing for making games and other type programs, is being able to capture the joystick. And in order to read the joysticks, we have to read the joysticks in 2 sets of axis. So joystick 0 and joystick 1 are the horizontal and vertical axis from one joystick, and joystick 2 and joystick 3 are the horizontal and vertical axis of the other. So these are actually kind of like system variables. Just like we can create our own variables to store information in memory, this is information that's already in your computer's memory that we will pull from. So when we read the value of the joystick, it is reading from hardware where our joystick goes. We're reading this from some location in memory. So joystick 0 and joystick 1 are the horizontal and vertical, the X and Y coordinates of one joystick. And so there's a little demo that printed them on the screen, but I found that demo to be less useful than the one I'm going to show you. So I'm going to show you my demo in just a second, but before I show you my demo, I'm also going to show you what they have us do here to determine if we have pressed our joystick buttons. There's also a paint program that the chapter came up with, and I've done one that's just a slightly better version of this. This was a very simple paint program. I want to jump ahead to the part where it's showing us how to read our joystick buttons. This part I actually never remembered doing, but again, the time I actually programmed in BASIC was well over 35 years ago. I don't remember having to peek into memory to see if the button was pressed. I remember, of course, I went on to use many other flavors of BASIC. I dabbled in Color Computer 3 BASIC, then I got into DOS BASIC, and I got into Quick BASIC and Visual BASIC. So I used many other flavors of BASIC, and I seem to remember there being a command called strig, which would pull the stick trigger values. And I don't remember peeking to get the buttons, but apparently in the older BASIC we had to do that. So what does it mean when you peek? You're actually looking into a location of memory. And so this is an actual spot somewhere in memory that is looking at the joystick interfaces and the joystick input. And so when we peek into this location, we're going to get back a certain number by what's going on in memory. And those different numbers are going to tell us whether or not the button is pressed. So according to this page here, if the button, if we get a number 255 or 127, that means nothing is being pressed, which is kind of like high middle values. If we go down one and we go to a 126 or 254, we've just gone down one number, that is telling us that we have pressed the right button for player 1. If we go down 2 more numbers and we go down to 125 or 253, that's telling us we pressed the left button, which is player 2, or whatever the case may be. But there's information here that basically will tell you if you press the button. So if you get a 126 or a 254, that means you've pressed a button. So I want to go back for just a second here, and I want to look at this original program here. This original program that I gave us had us read the value of the joysticks and print them on the screen, but it was printing it on the top line of the screen and I felt that just looking at numbers changing wasn't as useful. So what I did is I actually wrote a slightly custom program that will move around on the screen where you're at. So I called this program JoyPrint. So this one reads the joystick and prints it out on the screen. So the program is very similar, where I read the X and Y coordinates of what's going on to the screen. However, what I'm doing here is I'm looking for a horizontal position. Now what you have to realize is that the joystick goes from 0 to 63, and horizontally on my screen I've got from 0 to 32. So I take whatever X is and I divide that in half, and that's going to help me figure out what column I am on my text screen. It's a similar thing for the vertical position. Because the vertical is from 0 to 63 or 64 options and I only have 16 lines, I actually divide the vertical position by 4, but then I also have to add 32 characters to that, so I'm moving up and down on the screen. So I did a fancy little math here to figure out where the joystick was and translate that into screen locations using the print at command. And so you'll see here in just a second, as I move my joystick around, you're actually going to see on the screen the numbers are going to move with the joystick, so it's a little bit more visual. I also then included the peak to determine if I was pressing the left button or the right button on my controller, and I will print that on the screen as either LB for left button or RB for right button. So when I run this demo and I grab my joystick, and this is a challenge you run into when I'm doing this on an emulator, right? So the position is 32, 32. That's dead center. As I move the joystick to the left here, you see that the number changes. This is now showing me I'm in position 0, which is far left. And if I move the joystick up, that number there for my y-axis should start to go up. So 32, 32 is kind of dead center. As I go down now, 63 is the bottom of the joystick vertical axis. And then if I go to a hard right, 63 is the hard right axis too, and when I go hard left I'm at 0. So my horizontal is from 0 to the horizontal to the far left to 63 on the hard right. Of course the wrapping is just slightly off. And then my vertical, if I go straight I'm up, if I go straight up I'm at 0, and if I go straight down I'm at 63. And so as I move around here, I can kind of see what my horizontal and vertical axis is. And so I took the joystick numbers and I did a little bit of math to translate the X and Y coordinates to screen coordinates to help visualize where your X and Y was. You can see the horizontal is on the top, and then the vertical depends on where you are. Now if I press the button, whenever I press LB, that's my left button. Now if I press my right button, I'll get an RB. So because I'm doing this in an emulator, I've mapped both buttons to button A and button B on my Xbox controller here, just to simulate the two joystick buttons. Now I'm only reading one joystick because I really don't want to plug two joysticks into my computer to illustrate this concept, but the demonstration was actually written for a real computer with two joysticks. In the old days you got the Black Beauty joysticks in pairs, so you could plug in both your joysticks and run that demo that's in the book to see the numbers move around. So I'm not demonstrating both joysticks, but I think I'm doing a slightly better job here on showing you left button and right button detection, and showing you my X and Y coordinates moving around with the joysticks by reading that joystick value. And believe it or not, this is very difficult to do in an emulator, to read the joysticks. MAME's actually doing a really good job. When I used to do a lot of my old videos in VCC, and even now, it's really hard to get 0 and 0 in the top left hand corner using an Xbox controller. So see, I'm getting 0 and 7. So getting the corners with a PC, a modern PC controller, like I should be getting 63, 63, and it's really hard. I'm getting 58 and 60 and 54. So trying to get these corners is sometimes very difficult on an emulator. That's the price we pay using modern stuff. There's nothing better than running a real joystick on a real Coco. So your mileage may vary on the coordinates that you're going to get reading your joysticks, but understanding how they're read and understanding how to use that information is going to be really helpful in making games or graphics demos.
Between 1977 and 1994, Tandy and Radio Shack produced a wide array of prolific personal and business computers. Chances are you've used one. And now there's a new event designed to celebrate all of these computers in one place. Introducing Tandy Assembly. Come see your favorite computers, or maybe some that you missed. October 7th and 8th in Ohio's first capital city, Chillicothe. See presentations by TRS-80 creator Don French. Creator of Dog Star Adventure, Lance Miklas. And Scott Adams of Adventure International. For details, visit our webpage at www.tandyassembly.com. Some assembly is required.
And so, speaking of graphics demos, the chapter also has a little routine in here that lets you paint, and it basically figuring out your H and V positions. It's also figuring out that if you try to go too far down, because your y-axis or your vertical can actually go all the way through 63. So what it has to do is if you leave the bottom of the screen, it actually has you loop back to the top, which I found to be very confusing. So I found the demonstration that they gave you in the book was kind of okay, but it also, I felt it could just use a little bit more polish. So just a short little program, slight variation on what was in the book, but I felt I'm a visual person. If I can see it, I can understand it better. Let's look at a program I made called JoyPrint. And JoyPrint is very similar to the one in the book, but just a little bit cooler. When I list it out, it's really not that big, okay? It is not a big program, but here it is. We have the Joystick Paint program. We clear the screen as 0. Here's our main paint loop. All right, so we get our X for our joystick 0, we get our Y for our joystick 1. I make sure that the Y is not too tall, too high on the screen, and I make sure the Y doesn't leave the bottom of the screen. I'm actually telling Y to ignore the top 2 pixels because I'm using that position to print some text. I then also scan the keyboard. I'm looking for you to press a key, and I get the value of that key. And the reason why is I figured it'd be nice if we could change colors. So if I can press the numbers 1 through 8 on my keyboard, I will change the colors that I'm going to paint with, so I'm not always painting with the same color. Line 60 then prints all the coordinates on the screen so you can see what you're working with. Line 65, this is something I tried to do and I kind of fell a little bit short, but I wanted you to be able to move around with a little blinking pixel that did not erase the screen. This would be easier to do on the graphic screen than it is on the low-res screen, but I wanted your pixel to be kind of I wanted to set and then preset based on what color was there, so it would be a flashing pixel so you could see where you were. The problem is because these pixels are broken into that kind of quadrant, if I move into any of the quadrants there, I'm actually going to be resetting a pixel that was on. So I am accidentally erasing part of the screen, and I just didn't really want to feel like getting into the really heavy logic to fix it. This is a really cheesy demo, so I'm not going to try to make it super perfect. But the concept is you can move a flashing cursor around to see where you are before you start painting. The minute you pick a color, you can paint. I actually was thinking about making this joystick enabled where you can't paint until you press the joystick button. But again, that's taken more work than I have time to do today. So let's just take a look at what the demo looks like, and you'll see what Willis is talking about here. So you can see the green square right now. And what you're going to see here is if I move the square up and down, and it's kind of flashing, you can see my X and Y values move. So this is kind of dead center, where X is 32 and Y is 2. I didn't let Y go any higher. I can move Y all the way to the bottom, Y is 31. I can move X over to 0, X is at 0. I can move X to the far right, X is at 63. So right now, because my color is 0, it's not going to paint anything. What happens if I press like 3? I think 3 is blue. Now that I've pressed number 3 and color is 3, now it's painting in blue. Alright, well, what if I want to stop painting in blue? Press 9. 9 takes you back to color 0. And now I can kind of move around somewhere else on the screen. And now when I want to paint something white, I would press 5 for white. Now I can start painting a white with my joystick, right? So it's a real cheesy drawing picture. If I want to stop painting, press 9. 9, but you see how I'm accidentally erasing part of my picture. I think 2 is yellow, right? So now I'm going to draw in yellow, right? I can just start pressing keys on the keyboard. That's blue. 3 should be blue. 4 should be red. 5 is white. 6 is that ugly green. 7 is the purple. 8 is the orange, right? And one of the things that I realized it's very hard to do is it's hard to get things outside of dead center in the corners when you're using an emulator, right? Because the emulator and the PC joysticks are not as analog and as loosey-goosey as the Coco joysticks were. Coco joysticks were very cool precision analog sticks, and as we try to emulate these, we're losing a lot of the values here. But it's just a cool demo. It just does a little bit more than what the book gave us. The book stepped you through using your X and Y coordinates of your joystick and drawing in a single line. This would actually be a lot more responsive on a real Coco, which again I'm just too lazy to set up and mess with right now. So this is the emulated version of this. Now, again, this program's not very big, right? We clear the screen, we read the values, we make sure that Y is within values of the screen that won't generate an error by going too high or too low. X is always going to be perfect within the width of the screen. I'm scanning the keyboard. I'm getting the value of that. When you get value, you're basically trying to turn a text value, a text string, into a numeric value. And because anything I press on the keyboard that's not a number will automatically have no value, will have 0. But if I press 1, the value will be 1. So anytime I press a key, if that key has any value greater than 0, I change the value of my color. I then say, well, my color now equals that value. And then if I don't press any more keys, that color will remain the same. I've also added the ability to turn off color by saying if color is greater than 8. So if I press 9, 9 is turned color to 0, and then I'll stop setting my colors for that. For as long as color is 0, I won't set. How do I try to do this? Well, line 60 prints on the top left-hand corner of the screen, what's my X coordinate, what's my Y coordinate, what's my color value. Line 61 tries to get the point or get the color value of where my current cursor is. Line 65 says, well, if my color is 0, meaning color is off, then what I'm going to do is I'm going to take whatever the point value is of the pixel that's already there. I'll set that one time, and then I'm just going to reset the pixel to turn it off. I'm doing that blinking effect like the blinking eye demo is. So I'm creating this blinking cursor. And this would be cool if we were dealing with single pixels, but we're dealing with a shared block of 4 pixels. So this method here can actually be destructive, unfortunately, and I don't want to spend a lot of time trying to fix that. But line 66 says if your color is greater than 0, meaning you pressed 1, 2, 3, 4, 5, 6, 7, or 8, and I've set the value to that, I am now going to set at my X and Y coordinates the color there. So as I'm moving my joystick around, it will put color at those coordinates to where I move it to. And then line 30 just goes back to the main loop. So very small program, just a slight spin on what the book gave us. Just the kind of the cool feature to change colors and to move without painting. I think it would be kind of cool to take this a step further and say you're always moving and you're only painting when you hold down the joystick button. It just took more work than I had time to do today, so I think I've done a pretty good job demonstrating these concepts. And then last but not least, what I also did is I took a minute to do a little random demo. So I wrote a program called Random Set. And what this program does, very small, very short program, it is picking, and actually I need to fix something here because I realized in the course of doing this is that you can't actually set color 0, which is unfortunate. I thought I could actually set color 0, but it doesn't set color 0. So I have to pick a color between 1 and 8. I was hoping I could randomly sometimes pick 0 and just set a black pixel. It will not let me set a black pixel. It only resets black pixels from what my experimentation has shown me. But what do? I start off, I clear the screen, I pick a random X coordinate between 0 and 63, I pick a random Y coordinate between 0 and 31, I pick a random color between 1 and 8, And then I'm printing on the screen what these values are so you can see what the program's doing. And then I set them. So I pick this X coordinate, this Y coordinate, and this color, and I set it. And then I did put in a little thing here that says, all right, if you pick 25 out of 100, clear the screen and start over. Kind of like my old graphics demo did. Every now and then, let's just not have the screen get filled up forever. I think this is actually probably clearing too quickly. But what we're seeing here is we're picking random X and Y coordinates, we're picking random colors, and we are setting pixels on the screen quite randomly, and it's just kind of cool. It's a very low resolution graphics demo. Because we're dealing with ultra low resolution, it goes a little faster. What we don't have here is we don't have any of the fancy features like get and put and paint and circle and line and draw and p-copy. Because the amount of pixels are so few, I guess they just didn't want to worry about making those cool commands to work in low res. It would actually be very cool to do painting and circling in here just for craps and giggles to see what it looks like. But this is showing you how you can set a pixel on the screen. You need to have an X coordinate, a Y coordinate, and a color, and it will set it on there. You can use a reset to reverse that pixel back to black, and you can use the point command to get the color value of the current pixel location to see if it's on or off and see what color it is. This is useful especially in game logic for doing collision detection. And Chapter 23, pretty cool. What do you think of it? Let me know. And this floppy disk will be on my website. I will do a blog for this as well, explaining kind of everything that I did here too. So if you go to ogStevieStrow.com, you can click on the latest blog entry for this Chapter 23, and you can download the floppy image if you want to try this demo at home. Until then, I'm the original gamer, JoyStrow. Keep on playing with your Coco. Keep on doing something retro. You may be only young once, but you can be retro forever. And if you like retro merchandise, maybe go to my website, ogStevieStrow.com. While you're there, check out the merchandise link and maybe grab yourself a DVD of some of my Coco gameplay videos, or check out the t-shirts and coffee mugs featuring cool Coco artwork and other vintage retro imagery as well. You just might like it. Until the next video, we'll see you later. Peace out. Bye-bye. Long live the Coco. Hey, what's going on, everybody? It's me. It's original gamer JoyStrow. You know, gameplay goodness. Gameplay goodness. You know, gameplay goodness. All right, people. Gameplay goodness. Thank you so much. You know, there's my shark down there. There's Maggie. You know, gameplay goodness. Just do it. Gameplay goodness. Yeah. Just do it. Gameplay goodness.
Are you ready for this?
You know, gameplay.